We're going to pick up in this video where we left off in the last video. So in the last video we talked about water and what water does and how water behaves. And so what we're going to talk about first in this video are strong acids, but the same thing can be applied to strong bases. And so what we mean by a strong acid or a strong base is something that will completely dissociate in the presence of water. So in this example, hydrochloric acid is a strong base. So the question I want to ask first, and that we're going to look to calculate, is that what is the pH of a 1 times 10 to negative 2 molar solution of HCl? Right? And so one of the things that we need to talk about is something called the analytical concentration. So the analytical concentration of HCl can be written like this. Right? And it is 1 times 10 to the negative 2nd molar. But when we put that into water, what is the actual concentration of HCl? I'll let you guys have 2 seconds to think about it. If you answer it was 0, you would be correct. So why is the actual concentration of hydrochloric acid in water 0? And that's because when you put the hydrochloric acid in the water, it will completely dissociate. There's nothing left. And so because of this, we know that this, for strong acids, is equal to the analytical concentration of that strong acid. So in this case, it's going to be 1 times 10 to the negative 2nd molar. And if we do that and do the negative log, we know that the pH is going to be 2. So that's for strong acids. It's pretty straightforward. For strong bases, instead of H3O+, we're going to get OH- that we will then have to plug into our water equation. Sorry for the crowdedness of all of this. We're going to plug it into the water equation, and then we can calculate H3O+, or the concentration of hydrogens, from there. So let's think about this though. So we have a strong acid. We have HCl. Here's our beaker. We're going to put HCl into our beaker. And so what we get, so these protons are going to start at the top, and eventually they will move down to the bottom. And we can calculate this, right? And so then the acidity, it'll be more acidic going down to less acidic at the point where we just put in the hydrochloric acid. This lag, so there's a lag time. When we calculate the lag time, it is longer than expected, it's longer than the actual time it takes. So why? And this is why water is so important. We put that hydrochloric acid in on top, so we get a bunch of protons on the top. Well, here's a water molecule that is now hydrogen bonded to another water molecule that's hydrogen bonded to another water molecule, and so on and so forth. But what you see is that this proton will hop here, this proton will hop here, this proton will hop here. It's known as the quote-unquote proton hop. And because of this, the time with which the acidity or the flow of protons moves is a lot faster than what we would calculate. So that's strong acids and strong bases. What about weak acids and weak bases? What about them? So we know that weak acids and weak bases are not going to completely dissociate like strong acids or strong bases. And so because of this, because of the incomplete dissociation, the solution is part acid plus part base in a solution known as a conjugate acid-base pair. Right, so a conjugate acid-base pair. And so what happens is the acid, the part acid, it will take and remove this from the solution. The base will remove that from solution. And so what we can see are things will be in constant, or will be in equilibrium. So let's look at acetic acid, commonly known as vinegar. So here's the conjugate acid, here's the conjugate base. So we can, like what we talked about earlier, or in the previous video, get an equilibrium constant, right? And we know that it's products over reactants in this case. Now, this type of equilibrium constant for a weak acid, right? So the acid is written on the reactant side, that we know as Ka. Right? It's a dissociation constant for a weak acid. And so if we want to do, so we can take our Ka, I'm just going to move it over here. So we can take our Ka, and if we want to find pKa, all we have to do is the negative log of that Ka. And that's known as pKa. Now pKa is important. The lower the pKa, the higher tendency it is to dissociate its proton. And so this is how we use to compare different weak acids, is using the pKa. So, how do we calculate pH of a weak acid since we don't get complete dissociation? So, hopefully you guys are ready for a little bit of math. And then I will tell you, and what we'll probably end the video with, is a little shortcut on how we can make it a little bit easier. So, here's our equation for a weak acid. So HA is a weak acid, usually with the way we write it. I'm just going to start out like this. So equilibrium constant is going to be products over reactants. I'm going to multiply the concentration of H2O. It will move it to the other side. So now we have, KEQ times the concentration. We know that as KW, but we can also know that, because it is a constant, and since this equation, A minus times H3O plus over HA, is very similar to Ka. Now, in a weak acid, without much dissociation, we're going to see that this is going to be equal to this, because there's not much dissociation, so that the concentration of protons and the concentration of the conjugate base are going to be equal. So what we can do, we're also going to see one more thing. So let's go ahead and do these two steps at the same time. So we're going to see one more thing, and that's the concentration of HA. So our weak acid is going to equal our analytical concentration, right, the amount that we put in, minus whatever does dissociate. Because you will get some dissociation. And so whatever dissociates, we will lose that from our analytical concentration, and that's what our concentration of weak acid will be. And so what we can do is Ka is equal to H3O plus times H3O plus, because that's what we want to solve for. So what I'm doing is I'm going to plug this back into, actually let me change that color. We're going to plug that back into there. So now we get H3O plus times H3O plus divided by the analytical concentration minus H3O plus. I'm going to simplify this to H3O plus squared divided by analytical concentration of our weak acid minus our concentration of hydrogen ions. Now, let's go ahead and just move. So what we're going to do, and I will tell you what we're going to do, and then I will show you what we did on the next slide. But what I'm going to do is I'm going to move this side over to there. I'm going to multiply Ka by CHA. I'm going to multiply Ka by the H3O plus. So what it's going to look like is this. Oh, come on. There's that. Plus, whoops, not plus, minus Ka H3O plus is equal to H3O plus squared. Now, if you take quantitative analysis and you learn about these, you will see this again, and you will have to use this equation. And so what we're going to now do is take all of this and move it to the other side. And so we're going to get 0 equals H3O plus squared plus Ka H3O plus minus Ka CH, make that smaller, HA. If you look at this equation and you think about it, we have AX squared plus BX, and in this case it's minus, but usually we see it as plus C equals 0. We see a quadratic equation. Yay! So to calculate this, because this is what we want to find, because we were calculating the key, it's negative b plus or minus the square root of b squared minus 4ac, but in this case we have a negative c, so it's going to be a plus. Let's do that. This CHA times A, which is 1, all over 2A, A is 1, this. You always take the positive root, and if I were not nice, I would say we're done here. Or you'd have to use this to calculate the pH. However, let's come back over here, and we're going to look at this little equation right here. So I'm erasing everything else. Everything else is just noise. So we have this equation right here, where Ka is equal to H3O plus divided by the analytical concentration minus H3O plus. And actually what I might do is, after I erase this, I apologize for how long it's taking me, I will go and redraw this. CHA minus. So we have this. We get to this point. What happens if we made an assumption? right? We're going to assume that dissociation is not happening as much as we think it's happening. And so what we're going to assume is that this we're going to assume that this is about the same as this. Now, here are the assumptions. Here's when we can make this. We can make this when Ka is less than 1 times 10 to the negative third, right? Because the acid then isn't going to dissociate much. We can also make the assumption when the weak acid is actually relatively concentrated. Because what we want to know, because if it gets more dilute than 1 times 10 to the negative 8, then we have to start dealing with water and the ionization of water. We're not going to really worry about that. So if these are your two parameters, if your weak acid falls within there, and usually calculations in biochem they do, then you can use this simplifying assumption. And so what happens then is Ka is equal to H3O plus squared divided by CHA. So then we get KaCHA is equal to H3O plus squared. We can take the square root of everything. And so we have the square root of KaCHA is equal to H3O plus. And that's how we can find the pH of a weak base, or a weak acid. For a weak base, we substitute Ka for Kb. There is Kb, and then the concentration of your weak base. Here is the key. Here is the key to solving this equation and doing it correctly. This right here. Notice, it is Ka, not pKa. So if you are presented with a problem like this, remember, it is Ka and not pKa. So we're going to leave the story here, and in the next video, we're going to talk about buffers and why we care about weak acids and weak bases in biochemistry.
Because you know I'm all about that base, no acid. I'm all about that base, no acid. I'm all about that base, no acid. I'm all about that base, base. Yeah.